Hey everyone, welcome. Have you ever caught yourself just looking up at those massive power lines stretching for miles across the landscape and wondered, what's actually going on inside them? It's so easy to just see them as these static metal cables hanging there. But in reality, the electrical grid is this massive, totally invisible, and incredibly dynamic highway. Today, we're going to unpack the hidden physics buzzing literally right over our heads. Okay, let's dive into this.
To really ground ourselves here, let's start by looking at the macro journey of power. From the generating station all the way down to the wiring tucked inside your own home, power travels immense distances. And at every single stage, whether it's stepping up hundreds of thousands of volts to shoot across the country or stepping down at that familiar pole-mounted transformer outside your window, electricity is in constant, relentless motion. But as it travels these incredible distances, it gets subjected to some seriously intense physical forces.
So here is our roadmap for this explainer. First, we'll look at the anatomy of the grid. Then we'll map out the big three constants. After that, we'll tackle this quirky thing called the skin effect, zoom way in to look at flux linkages, and finally, we'll zoom back out to see how clever engineering solves it all. All right, Section 1, Anatomy of the Grid. Let's shift our focus away from those giant towers dominating the landscape and zoom right in on the actual physical lines carrying the current.
You see, when engineers look at a transmission line, they absolutely do not just see a simple, empty pipe for electricity. Not at all. A transmission line actually has specific electrical parameters, which are resistance, inductance, and capacitance, and these are uniformly distributed along its entire length. So no matter how ridiculously long that wire is, these forces are constantly at play, spread completely evenly from one tower to the very next. Moving on to Section 2, the big three constants. This is where we explicitly identify the specific physical forces that engineers absolutely have to calculate for every single line they string up. We call these the big three parameters of the grid. We're talking resistance, inductance, and capacitance. Working together, these three constants dictate exactly how electricity is going to behave as it travels those massive cross-country distances. Let's quickly break them down. First up is resistance. You can basically think of this as the inherent electrical friction within the wire. It's just the natural opposition to current flow. And it's entirely dependent on the specific material of the conductor and its dimensions, meaning how long it is and how thick it is. The thing to remember is, even the absolute best conductors in the world have some fundamental friction that engineers just have to account for. Next, we have inductance. And honestly, this one is pretty wild. When alternating current flows, it doesn't just quietly move forward. It actually creates a changing magnetic flux that links back to the wire itself. Because the current is constantly alternating, it creates these varying magnetic fields. So it's essentially building its own invisible magnetic hurdles that the power has to constantly push through. The third parameter is capacitance. Now, a capacitor is naturally created whenever you have two conductors separated by some kind of insulating material. So, in the case of a giant overhead transmission line, what exactly is the insulator? Well, it's the open air itself. Because these high-voltage lines are separated by nothing but air, capacitance naturally exists between any two parallel conductors just hanging out there on the towers. Pretty cool, right? Okay, Section 3, the skin effect. Let's look at a very specific kind of quirky behavioral problem caused solely by the fact that we use alternating current. And this brilliantly illustrates the issue. If you have a steady direct current, or DC, it flows perfectly and uniformly through the entire cross-section of the wire. But alternating current, it doesn't do that. It has a really strong tendency to concentrate near the outer surface of the conductor. It basically creates a sort of traffic jam right on the outer perimeter, leaving the center of the wire relatively empty. So why exactly does this happen? Well, imagine a solid wire as just a bunch of tiny inner strands. The strands near the dead center are surrounded by a greater magnetic flux. This higher inductance acts as a stronger resistance, or reactance, and literally pushes the alternating current outward toward the surface. The result? The effective usable area of the wire is actually reduced, which slightly bumps up the overall electrical friction. And this effect gets worse depending on the material, if you're using a larger diameter wire, a higher frequency, or if the wire is a solid piece rather than a bundle of strands. Luckily, engineers have precise mathematical thresholds where they can just safely ignore this crowding effect. The skin effect is considered totally negligible when the supply frequency is relatively low, so under 50 Hertz, and when the conductor diameter is small, specifically under 1 centimeter. But when we're talking about those massive grid lines, it's a major factor they absolutely have to manage.
Section 4, flux linkages and inductance. Let's zoom way, way down from the macroscopic tower view into the subatomic invisible forces interacting in and around these parallel wires.
Now, what's really interesting about this slide is that the magnetic field isn't just this aura floating completely outside the wire. To find the exact inductance, engineers have to map the flex linkages, which actually link internally within the conductor itself, radiating from the very center outward. It's this incredibly complex web of internal flux that heavily influences how efficiently the grid operates.
We also have to look down at the ground. We established earlier that air acts as an insulator between wires, right? Well, the Earth itself also acts as an opposing plate. That means there is actual capacitance between the transmission lines and the ground. Technically, the effect of the Earth is to increase capacitance. But for all practical purposes, because those massive towers hold the conductors so incredibly high up compared to the distance between the wires themselves, engineers can largely just ignore the Earth's effect in their daily calculations.
But here is the major problem. We've got multiple parallel lines, all creating mutual magnetic fields, all linking with one another. So what happens when these invisible forces throw the grid out of balance? Well, if the flux linkages and inductance of each phase aren't exactly the same, it results in unequal voltage drops across the phases. Even if the current is perfectly balanced at the start, your receiving end voltage gets completely thrown off. And why does this matter? Because ignoring these forces would lead to massive power grid failures and catastrophic blackouts. The stakes are literally incredibly high.
Which brings us to Section 5, engineering the solution. Let's zoom back out to the macroscopic view and see how human ingenuity actually outsmarts these physics to prevent those blackouts. If you string up 3 lines asymmetrically, meaning they just aren't perfectly equidistant from one another, the mutual inductance effects of the different phases start to clash. The flux linkages become unbalanced, causing those severe, dangerous voltage drops we just talked about. But to fix this, engineers implement a really brilliant, highly effective solution that stabilizes the entire transmission network. That solution is called transposition. Transposition means they quite literally exchange the physical positions of the conductors at regular intervals along the line. Over a specific distance, the wire on the left crosses over to the middle moves over to the right, and the right swings all the way to the left. By the end of the run, every single conductor has occupied the original position of every other conductor for an equal distance. This perfectly, elegantly balances out all those unequal flux linkages. To map this out mathematically, engineers use a concept called geometric mean distance, or GMD. There's self-GMD, which is strictly dependent on the physical size and shape of the individual conductor itself. But then there's mutual GMD. So the crucial point is that the mutual interference between wires doesn't depend on the exact size or shape of the wire at all. It relies entirely on the geometric space between them. Spacing is everything here. It's pretty amazing when you step back and think about it. Sometimes the ultimate solution to complex subatomic physics and invisible magnetic flux isn't some magical new material. It's simply a matter of geometrically rearranging the wires in the sky, transposing them so they all share the burden equally. It really makes you wonder, the next time you drive past those massive towers, just how much hidden, elegant engineering is quietly humming right above our heads. Thank you so much for joining me on this explainer, and as always, keep your curiosity sparked.